Hello, everyone. First, I would like to thank you for giving me opportunity to say a few words today. My talk is about variable selection in high-dimensional statistics, which is, I think, quite important problem, especially if you work with data sets containing many predictors. If you are able to find significant predictors in your model, then it might be really important, maybe sometimes more important than good prediction or good estimation. In the talk, I will focus on two procedures which are used to find variables, significant variables. The first one is quite well known. The second is maybe is rather new, and they both are fast, which means that they can be computed. They can be computed easily. They are not time-consuming, and moreover, they are robust, which means that they are robust with, for instance, outliers which can appear in the sample, or they are robust with respect to some link function that I will show you in a second. And I'm going to present some theoretical results about these procedures as well as some experimental results. My talk is based on two papers. The first one is with Gosia, and the second is with Konrad Furmańczyk from Warsaw. Let's start with the model that I will focus on. This is sometimes called in the literature a single index model, and we've got response variables, which is denoted by y. We've got vector of predictors. So in our model, there are p predictors. Beta is a true parameter. And we also have random errors. And there is a function g, which is unknown. So our model is like that. So the relation between predictors and response variables is given by the scalar product of beta times x, which is sometimes called index. And there is also a function g, which we assume that is unknown. And since this function is unknown, then we cannot use this function in the estimation process. And we will try to do it using another tools. So maybe a few examples of this model. So for instance, the linear model, but as well you can use the modified linear model. You can modify your response, or you can modify just this scalar product. So these all examples are examples of models with additive noise. However, the noise need not be additive. We can as well consider binary regression. Let's say that our labels are 0, 1, and the probability of being 1 given predictors is defined by some function which is unknown as well, and the scalar product of beta times x. So for instance, the logistic model is here, the probit model is here. However, usually when you use the logistic model, then in your estimation you use the fact that the probability function is like that. We will not use this knowledge. And that's why I will call it robust with respect to the function g. And our task is to find relevant predictors in the model, which are defined by T. So this is the set of coordinates of the parameter beta, which are non-zero. And we want to do it in the high-dimensional case. So the number of predictors, P, can be much larger than the sample size. Of course, the function g is unknown, so my parameter beta is not identifiable. I mean, when we come back here, for instance, then the intercept in beta cannot be recognized because it can be absorbed by the function g. Any scale change in this product also can be absorbed by g. So in general, my parameter beta is not identifiable, but my task is not to find this parameter. My task is to find this set T. So first, I do not need the intercept of beta. It gives me nothing. And in fact, I'm not interested in estimating magnitudes of beta. I just want to know if they are zero or non-zero. And I will show you that under some not restrictive assumptions, we can recognize this, vector beta using our procedures with respect to positive multiplicative constant, which is enough to be able to select the set T, to find the set T. Summarizing, this is our model. We put no assumptions on distribution of errors, existence of their moment, and moments and so on. We assume that function g is unknown. All we need from theoretical point of view, not from the estimation point of view, but from theoretical point of view, we only need that this function is increasing with respect to the first variable, which is related to predictors. We do not assume anything about the second variable. And if we go to binary regression, then we also do not need the function g. All we need from the theoretical point of view to prove some theorems, we will need that this function is increasing. Okay, and we want to find the procedures which are robust in variable selection, robust with respect to the distribution of errors, with respect to this function g from here. But we also want that these procedures to be fast, I mean computationally fast, to be able to work in with high dimensional data, to be able to compute estimator without much effort. Okay, so this is our problem. So if we focus for a second on the linear model in high dimensional case, then there is a very popular procedure called Lasso, which is about minimizing the sum of risk and the sum of penalty, where the penalty is the L1 norm. I think you are quite familiar with the Lasso estimator. During our seminars, it was mentioned several times. So I'm not going to present any properties of this standard estimator, but I will show you. I want to tell you that we expect that, for instance, there might be outliers in our sample, and in such a case, it is not a good idea to use this standard version of Lasso, because the loss, which is quadratic here, is very sensitive with respect to outliers, and this estimator will not work properly. What people do is to try to find some robust procedure, which can be, for instance, the Lasso, which is the least absolute deviation estimator with the penalty. So I think the easiest we can do, we just replace the quadratic loss by the absolute value loss, which is robust with respect to outliers, and the penalty is the same. So this procedure is quite nice. As I told you, it is robust, but the problem with this procedure is that it is time-consuming. I mean, even if you've got, for instance, 1,000 predictors, then this procedure works very slowly when you compare it to this estimator with the quadratic loss. Okay, so that's the problem. I would like to find the procedure which is robust, but which is also computationally fast. And our proposition is quite simple. It is related to ranks. Ranks are very well known, and they were used in non-parametric statistics many times. They are robust, of course. They were used, for instance, to develop Wilcoxon tests and other procedures. And this is our task, to involve ranks in the estimation process. So what we do is we take our response variables, then we sort them. So this is the smallest one, the second smallest, the third smallest, and so on. And then we assign ranks. So this is the rank of the first object. So this is the number of Y1 in this sequence, and so on. And our procedure is extremely simple. We use the Lasso, but here, instead of the risk, we put the same risk as in the standard Lasso. So this is the quadratic function. However, instead of response variables, we put ranks. In fact, these are ranks divided by n, so they are on the interval 0, 1. And we call this procedure the rank Lasso. So all we need is replacing response variables by ranks. So I think it's rather clear that this procedure is computationally fast. You do not need any new algorithms. You can use, for instance, the Lars algorithm or the GLMNet package in R. So you can calculate this estimator very quickly. But this procedure is also robust with respect to outliers because we used ranks. And in the estimation process, we do not need the function g. Okay, but the problem is that I think it's clear that when I use this estimator, which we call rank Lasso, then I do not estimate the parameter beta, but some other vector. And the problem is how is this new vector, which is estimated, how this new vector is related to the parameter beta. And I will show you in a second this relation. But first, I will give you the second procedure, which works in the binary regression. So generally speaking, if you work with high-dimensional data, which are taken from binary regression, then first thing you do is the logistic regression with Lasso. So here you've got the negative log likelihood. And here we've got again the penalty, the Lasso penalty. So you do it because first it works quickly, quite quickly, using, for instance, the GLMNet. The second reason is that you have the nice interpretation of coefficients of beta. But okay, if you want to do logistic regression, then why not do something else, which is quite well known, This is just taking your labels and putting here into the standard Lasso. So we take 0, 1 and put here. And you can do it very quickly, much quicker than the logistic regression. And this procedure is very well known. It was used in, for instance, in these books to analyze some real data. But in fact, this procedure comes, I think, from the Fisher, from the many years ago. Of course, he didn't work in high-dimensional case. He didn't consider Lasso penalty, but his linear discriminant analysis was just about that, putting 0, 1 labels instead of response variables and using ordinary least square estimator. Okay, so this procedure is not new, but people use it, and we want to find out why this procedure can give you good results, in what situations, what assumptions are needed for your data to give you good results. Okay, so again, it is computationally fast and so on, but again, we do not know in fact what we estimate using this procedure. For sure, we do not estimate the parameter beta. Okay, so first, I will give you a relation between the parameter which is estimated here in the binary regression case and the beta. So if we forget about the Lasso penalty, then we minimize something like that. So I think it's rather clear that the vector that we estimate, which I denote by theta 0, is the minimizer of the expectation of this risk. So the risk is random, but we take the expectation, so this vector is deterministic, and this is the vector that we estimate. But the relation between, of course, we can easily calculate it, but what is the relation between the parameter beta and this vector? It's not clear. In the second case, for the rank Lasso, you can as well define your estimator as the minimizer of the expectation of the risk, but again, the relation, you have to think about the relation between your parameter beta and this new vector which is estimated. Okay, so in fact, these both procedures, I mean the rank Lasso and the procedure in the binary regression case, can be in some sense considered simultaneously, and our theoretical results works more or less for both of them. So first, assumptions which gives you the relation between the true parameter and the parameter we estimate. So we assume that our data are IID. Just for simplicity, I assume that predictors are centered. And the next assumption is that my covariance matrix is positive definite. So this is not the empirical covariance matrix, but this is the population covariance matrix. So this assumption is not restrictive. But there is one more assumption which is important, and it says that for each p-dimensional parameter, we consider such conditional expectation, and we assume that this conditional expectation of theta times x given beta times x is beta times x times some number which can depend on the parameter theta. So roughly speaking, you can say that the regression of theta times x on beta times x is is linear in beta times x. Maybe it's not very formal because this number can depend on theta, but you can think like that. Okay, this condition is also not new. It was used in statistics, I think, in the 80s and maybe even in 70s. You can easily prove that it is satisfied, for instance, when you have only one predictor, but maybe it is not important example. But you can also prove that this condition is satisfied where you work with quite a large family of distributions called elliptical. For instance, the multivariate normal distribution is in this class, all T distributions are in this class. So this condition is satisfied in such cases when your predictors are sufficiently regular. But there is also a paper of Holland Lee where they prove that asymptotically when P goes to infinity, this condition, the linear regression, the linear expectation, is satisfied or almost satisfied when P goes to infinity. So it looks like this condition is not restrictive when P is large, and this condition when P is large is really the case that we are interested in. I mean, we are interested in high-dimensional scenarios. So these are conditions which allows me to give you the relation between theta 0 and the parameter beta j. I mean, if these four assumptions are satisfied, then...
Can I have a question?
Yeah.
So is the whole and the other co-after result valid for the case when n is less or equal to p as well?
Yes, it is. But here, for instance, in this condition, there is nothing about n.
Okay.
Okay? There is something about n, of course, here, but it works. For instance, if your distribution of predictors is elliptical, then it works for each p. So, for instance, when p is smaller than n also.
Okay, so yeah, okay. But so I'm not. I try to imagine what the result says there, because you said asymptotically when p goes to infinity for what? For any distribution or what?
No. This is just about p. Here you do not have any n.
Yes, but what is the result from the paper you said that you said?
You mean this paper?
Yeah.
I don't remember exactly, but they say that in some sense when p goes to infinity, then here you have this function is linear or very close to be linear.
This is regarding the distribution of x.
Yes. Okay. Yes. Only when you have many predictors.
Okay, thank you.
Okay. Okay. So if these assumptions are satisfied, then we have the following relation. I mean, there exists some positive parameter gamma, such that on each predictor, the parameter that I estimate is proportional to the coordinate of the parameter beta, and this number is positive. So in particular, it means that the support of beta, which is the set of non-zero coordinates of beta, is exactly the same as the support of the parameter I estimate, the vector I estimate. Okay, so if I am able to find which coordinates of this parameter are non-zero, then I am able to find out which coordinates of this vector are non-zero, and if I am able to do it, then I am able to find relevant predictors in my model. Okay, so this is about the binary regression, and about the procedure which uses ranks. We have the same assumptions. What we need more? We need, again, that G is increasing with respect to the first variable, and we need that the distribution function of Y is increasing. In general, it is non-decreasing, but we need that it is increasing, so this is not restrictive. And then we have very similar claim. I mean, the parameter that I estimate is on every coordinate proportional to the parameter that gives me relevant variables. So again, using the procedure which is based on ranks, I am able to find the relevant variables in the model. So using these two procedures, I'm able to find the relevant predictors and irrelevant predictors in my model. Okay. Few general remarks about my procedures, our procedures, is that as many Lasso estimators, we can prove that they are variable selection consistent if some restrictive assumption, some additional restrictive assumption is satisfied, which is called the irrepresentable condition. And under much weaker condition, we can prove screening, which is the case that this is the support of my estimator. So all the relevant predictors are selected by my estimator, and possibly we have also some false discoveries, some irrelevant predictors. But we are also able to prove the separability of predictors, which means that on coordinates, my estimator on coordinates which corresponds to the true predictors, it is larger with respect to absolute value, of course. It is larger than coordinates of my estimator which correspond to the irrelevant predictors. So this is called separability. I am able to separate irrelevant predictors from the relevant predictors. But the important feature of our procedures is that in the binary regression, we do not need the function G to be known. All we need that it is increasing. And in the single index model, in the case that Y is real, for instance, we do not need any assumptions on the distribution of errors. And in fact, we also do not need the function G. So this, I will show you in a second the result, which is about separability, which is crucial property. And if you have something like that, then you can prove, for instance, that you can find the true predictors using the thresholded lasso, which is you just cut your estimator on some level, or you can use the two-step procedure with weights to find the relevant predictors. But the crucial property is the separability, and I will show you one result, theoretical result about that. One more thing. The theoretical analysis of the procedure in the binary case is quite similar to standard proofs of Lasso estimators. Of course, you have to overcome some problems with misspecification of the model, but it is not difficult. Situation is a little bit more difficult when you work with rank Lasso, because when you use ranks, then Here the risk is not the sum of independent variables, it becomes a sum of dependent variables. However, if you use the theory of statistics, then you can overcome this problem as well. So this is a few words about proofs, but the theorem is like that. We have two numbers, A and Q. We additionally assume that our predictors are sub-Gaussian, which is quite standard condition if you work in the high-dimensional case and if your predictors are random. You assume as well that the cone invertibility condition is satisfied. This is also a standard condition, which is about the correlation between predictors, I would say. Maybe I will skip the details about that. You also need that your sample size is large enough, which is given here. K1 is some number. P0 is the number of relevant predicts in your model. So you've got here P0 squared, and here you've got the logarithm of P divided by A. Then your tuning parameter in the Lasso penalty has to be large enough, and as usually it is like the square root of log P by N. And then with probability which is close to 1, if you take A close to 0, you can bound the estimation error in the LQ norm, the difference between your estimator and your parameter. You can bound it by, again, some number times P0 to the power of 1 over Q and lambda. So the message from this theorem is that this estimation error is small if your model is sparse, which means that P0 is relatively small, and if lambda is also small. Lambda is given here, this is the lower bound, so it should be small. As you can see, this will be small even if the number of predictors depends polynomially on n, or even if it depends exponentially with some small exponent on n, so it works in the high-dimensional case. So if you look on this result and you are quite familiar with Lasso estimators, then you can think that this is very similar to the standard Lasso estimators, but I think I have to stress that this is under no assumptions about the distribution of errors, and we do not need to know what is the function g. Okay, so this is the main difference with the standard results about Lasso estimators. Okay, so if you have something like that, then separability is very close. I mean, if you assume that your smallest non-zero coordinate of beta is denoted by beta mean, then our estimators can separate predictors if beta mean is larger than such thing. So here some number times lambda, which is the tuning parameter, and here we got gamma. And again, for instance, if the linear model in the linear model with Lasso penalty, you would have very similar result like here, but there is no gamma in the denominator, of course. In our model, the parameter gamma is usually smaller than 1. So this is the price that we have to pay for using these procedures based on ranks or replacing putting response variables into the standard Lasso. So we need something more. You can translate it into the fact, for instance, that the sample size has to be larger. So if you use our predictors, you obtain computationally fast methods, which are robust, but of course you have to pay some price, and this price is more or less than your sample size has to be larger than in the case that you know, for instance, that your model is a linear model and your variance is finite. So this is the consequence of our theorems, and I think I've got some time, so I can show you a few experiments, results of experiments. So first, we assume that our model is linear. Predictors are normally distributed. They can be independent or dependent with correlation 0.3. Errors are Cauchy distributed, so there are some outliers in our model. This is the true parameter. So we have at the beginning a few relevant predictors, 3 or 10 or 20 relevant predictors, and then we have relevant predictors. The sample size is like that. The number of predictors is like that. So if n is 100, then p is also 100. If n is 200, then p is 400, and so on. So we've got 4 scenarios, and as you can see, the number of predictors is larger than the sample size. We consider few estimators. The first one is the rank Lasso with the tuning parameter with the constant 0.3 in each experiment. And then we have adaptive rank Lasso, so we use the two-step procedure. We have also thresholded rank Lasso, so we just cut our estimator on some level. We have also the competitor, which is the Lasso with the penalty with a constant 1.5. And finally, we use the standard Lasso for linear regression with the tuning parameter chosen on the basis of cross-validation. And we repeated our experiments many times, and we calculated something which is called NWDD, which is the number of wrong decisions. I mean, this is how many times, on average, how many times I selected a irrelevant predictor, or I discard the irrelevant predictor. Or I discard relevant predictor. So this is a number of false discoveries and then plus the number of false rejections. So how many times I make a mistake. And this is the first picture. Here we've got independent predictors, 3 relevant predictors. Here we've got P. P increases, so as P increases, then also the sample size increases, so I get more and more information on my data. Here is the number of mistakes I make. The red one is rank Lasso, then we have thresholded, adaptive, Lasso with cross-validation, and Lasso. So as you can see, for instance, Lasso with cross-validation, it is not able to select any predictors. It discards all of them, so it makes 3 mistakes, about 3 mistakes. These robust procedures are much better. They do not make almost no mistakes. If we take 10 relevant, if we consider 10 relevant predictors, then situation is quite similar. However, as you can see, rank Lasso is much better than Lasso. And here you've got our modifications of rank Lasso, the thresholded and the adaptive. There are two lines here, however, they are very similar, so we can see only one of them. And if we take 20 relevant predictors, then it becomes like that. So again, modifications of Lasso are better than rank Lasso and better than Lasso. If we go to the model where predictors are correlated, then both estimators based on Lasso penalty, the rank Lasso and Lasso, they are not able to find the true model. It is well known because they are able to find significant predictors, but they make many false discoveries. But at the same time, modifications of Lasso works very well. If you have more relevant predictors, then you can see very similar pictures. And finally, I think okay, maybe very quickly I will show you experiments in the nonlinear case. You've got the exponential model. The rest is pretty the same. So we've got outliers here, and using the rank Lasso, we do not use the knowledge that my model is exponential. And as you can see, this is the case where predictors are correlated. Again, of course, Lasso estimators are not able to find the true model, but at the same time, modifications of rank Lasso works very well. Okay. There are also some other results, but maybe I will. I think my time is up, so maybe I will finish now. There are some papers, and thank you.